Hello, this is Andy Schweitzer. Going to put together a little video here on Gibbs free energy. A couple questions that will be highlighted here in the Gibbs free energy will be what is Gibbs free energy? How do I calculate Gibbs free energy? And what is the relationship between Gibbs free energy and equilibrium? Okay, couple of things here. I'll grab a marker here. All right, so what is Gibbs free energy? Okay, well, Gibbs free energy is its total net loss or gain of a chemical reaction. Loss or gain. Now, you have to understand that if we were to take this in human terms, you know, let's say a ball on the top of a hill, and it has a very high amount of energy, and it rolls down the hill to form a small amount of energy. So this ball already contains the high potential energy, and as you give it a little bit of activation energy of activation, then you would just simply roll on its own unimpeded until you get to the bottom. Same thing here when you're referring to a chemical. The reactants, and we often draw an energy diagram like this, have very relatively high energy, a little bit of activation energy, and then it is allowed to flow freely towards products. They already contain the energy, just need to release it. So if your system is going to be losing energy, it would have a net loss energy, therefore delta G is negative. And then if your system needs to gain energy in order to run, it would be overall positive delta G. Gibbs free energy contains two items. One would be your delta H energy and your delta S energy. And we'll show some mathematics of that in a little bit. But just understand that for a reaction to run, it would need to lose energy on its own to run on its own. If a reaction needs to absorb energy from the surroundings, then this reaction will sit, a ball will sit on the bottom of this hill indefinitely until something applies the energy to bring it back up the hill. So that would be a non-spontaneous reaction versus a spontaneous reaction. All right. Now, in this case, one thing you want to kind of understand is that if I have a reaction and what I've indicated is my reactants, pour some in here, and it will, if it flows towards, let's say, my products, okay, then my delta G will be negative. So in this case, a negative delta G indicates a reaction that flows spontaneously towards products. So if I have, again, I always draw this out, reactants versus products, and if this is my end point, okay, or I would also say my K, my end point, my equilibrium point, or I could go all the way to to ending, and Q is my starting point. That if my G is negative, that means I will flow to the right, all right, to get to my end point. Okay. If delta G is positive, that means what I've designated as my reactants and what I've designated my products, I won't be flowing to the right. Okay. If I draw out my little diagram again, and this is all drawn out already, but you can pause the video and catch up with me if you want to, for note purposes. But that means that if a balance between products and reactants, my end point is again my K right here, that I happen to be given a starting point that is heavily loaded towards products, I'm actually going to flow to the left. For what I've designated my reactants, what I've designated my products, I will be flowing to the reactants. Now, there is also the possibility that my delta G equals 0. All right. In this case, what I've designated as my end point, whether it's right here, or it could be at the actual completion point here, or it could be highly reactant favored, that wherever my end point is where I currently have. My ratio of reactants to products is at that point, and I ain't going nowhere. I may still have a shift of reactants to products, but there's no net change in my concentrations and concentrated products. I might be going back and forth, but there's no net change. I'm going back and forth evenly. We measure delta G in a unit called kilojoules per mole of the reaction cycling through. So as you look at this scenario, I like to be able to understand the magnitude of delta G and where I am on my reaction cycle. So keep in mind that if this is your end point at K, I'm basically that's my ending point, then as I pull my reaction back, meaning I start to crank up my concentration of my reactants. So I'm dumping in a whole bunch of reactants. I have mostly reactants, very few products. My delta G now becomes negative because I will flow to the right in order to get back to my end point. As I pull back farther and farther, meaning I add more and more and more reactants, then my delta G gets bigger and bigger and bigger negative-wise. Okay. Conversely, as I pull it back to the right, I have a positive delta G, and the farther I could pull it this way means that my concentration of my reactants are picking up higher and higher and higher, and I get a larger and larger positive delta G, and therefore it would eventually spring back, give an opportunity towards my end point, in this case to the left. Okay. Delta G, of course, is every time this thing cycles through. If I have this reaction, 1 mole of this and 2 moles of that, it's 1 mole of this gives me delta G, and it just gives it to you in kilojoules. It doesn't say per mole, but it means per cycle through of the reaction. Per 1 mole of this, 2 of this, and 1 of these. So I always like to be able to relate Gibbs free energy. What does it mean, delta G? Okay, it's total net loss of energy. Along with this, I will jump right to my third question is, what is the relationship between Gibbs free energy and equilibrium? And then we'll take a moment and look at how you actually calculate this thing. Okay. So flipping over here to equilibrium. Now, equilibrium, okay, and again, if you're, depending on how much knowledge you have of chemistry, you should know that a reaction either can go to completion all the way to the end, or it can go to it can stop somewhere along the spectrum. And if my end point is right here, I call it K. K is my equilibrium endpoint. And of course, this would be product favorite. So I draw the line straight up just to represent what I call STP, my standards starting place, is sometimes how I call it, but it stands for standard temperature and pressure, standard starting place. Now, in this case, if this spot never changes, if different reactions might have different endpoints, I might be over here, I might be over here, but if I'm starting from right here and I'm looking at a product favored reaction, delta G will be negative, and the magnitude of that negative is depending on how far down my K is. So that means the farther the K is down here, the more I had to pull it back to get to my STP. So there is a relationship between delta G prime, my standard starting point, and where my ending point is. Over here I have it drawn as well, is that we have my my K point right here. Again, either side, this is my starting point. It'll flow this way to achieve that K. It'll flow this way to achieve that K. I would have a negative delta G here, and I'd have a positive delta G if I'm going in this direction. So there is a relationship between the magnitude and the sign, and here is that relationship right here. Delta G prime equals negative RT, natural log of K. You look on your laminated sheet and you'll find a K value which is 8.31 joules per mole Kelvin. You want to know where that is. And this is in kilojoules, so in this case I am going to bump this thing up to kilojoules per mole Kelvin, 0.00831. At this point it's simply a plug and chug situation. You plug in your K value and you can find your delta G prime, or delta G prime, you can find your K. If we're dealing with electrical potential, then we have another situation here. Again, electric potential was highlighted in electrochemistry, but it represents something very similar to delta G. It tells you how much energy we need or we'll get back as we approach equilibrium. Okay. I'm not going to go through how to plug numbers in. You can look at that on your own. Now, there is a difference between two things here, and there's delta G and delta G prime. Delta G prime means we're starting from this common starting point. I often put it straight up and down. Delta G prime, okay? That means, again, a ratio of concentrations of reactants versus concentrations of products, that they're 1 molar and 1 molar. That gives me delta G prime. And I can go in either way to achieve my equilibrium, whichever it may have to be. Now, if I were to crank up my concentration of my reactants, hypothetically, rank them up, and then therefore, conversely, proportionally, this would go down, I would have a new delta G. And if this is my endpoint right here, you should be aware that delta G is going to get increasingly negative as I get farther and farther from my K. But what is that delta G? It's delta G with a non-standard, okay, non-standard. That is this guy. And this is the equation that we'll use to calculate. This is off your laminated sheet from your AP class. I have my delta G, new delta G, non-standard, equals my delta G prime plus RT natural log of K. R, again, is your gas universal constant. Temperature, you could plug in. And natural log of Q. Q, of course, is your equilibrium reaction quotient. It is calculated like, well, we've learned about how to calculate that array, but it's just a ratio of products or reactants. You may have some powers involved here. And that gets plugged in here. Of course, as this thing gets pulled off of my K to my standard, we'd have this guy. And you use your charts to figure that initial standard starting point. Pull back farther, delta G gets even bigger and bigger and bigger. And then, of course, we get this guy. And if you want to calculate it, there's an alternate equation using a log version instead of a natural log. But either way, if I were to pull it back, I would let it run on its own, given some time, would flow back towards products. Eventually, then the reactants would drop, products would pick up. I would pass through my starting standard point. At that point, my delta G could be calculated. But again, and I can let it continue, and once I leave that standard point, I'm once again back to a non-standard delta G. All right, could be calculated off this equation. This equation generally is used for how to change my concentrations. I've seen problems ask about temperature. They generally use this equation for altering temperature. They just plug a new temperature in right here. Okay, that is delta G and equilibrium. We're going to take a moment here and in the next little video look at how we actually calculate delta G standard. Okay, now this is how we'd calculate delta G non-standard. Most times we're calculating as a standard point. So I'm just going to walk through quickly how we use our charts to calculate out a standard delta G. Thank you.